So let's try to plot the temperature-specific entropy, the second stage Hirn cycle with 3 extractions that we have been presenting before. So on the TS diagram, we find again the saturation line. We have now 5 different levels of pressure in the system: the high pressure, the low pressure, and also the 3 intermediate pressure that corresponds to PS1 for the pressure of extraction 1, PS2, PS3 for the 2 other extractions. We also have the maximal temperature that we have at the inlet of the turbine, and we have at the inlet of turbine point A, which is at high pressure and maximal temperature up there. Then we can, as usual, plot B is the ideal and isentropic outlet of the turbine we would get with the adiabatic reversible expansion, and on the real expansion there is the entropic creation, so point B is at a higher specific entropy, and we can schematically consider that we have line that will directly connect point A and point B to estimate what is taking place during the expansion from the inlet to the outlet of the turbine. Then the cross section between this line and the 3 intermediate pressure corresponding to the extraction pressures will set what is the thermodynamic state of the 3 points corresponding to the extraction. So that would be the point S1, this would be S2, and this will correspond to S3. Now, the fluid that is going out of the turbine in B will first go through the condenser and give heat to the secondary fluid of the condenser, be fully condensed until being a saturated liquid in the point that has been called C1. Then the first pump will increase the pressure from C1 to what's called D1, and D1 would be at the pressure PS1, and so almost merge we have point D1, which is similar to C1 but at a higher pressure for the pressure of extraction S1. Then we have a mixture between the flow from D1 and the extraction that is taken at state S1. When both fluids are mixed, of course they are at the same pressure. That's necessary in order to do the mixture, and the thermodynamic state of the mixture will be state that is in between both states, depending on the respective flow rate we have from D1 and from S1. Of course, S1 is an extraction, so by definition it's a small amount that was extracted, so the mass flow rate of S1 is much smaller than the mass flow rate we have from point D1. So the mixture will be somewhere on PS1 but much closer to D1 than S2. So for example, we can consider that we have somewhere there the mixture that was written as point C2. So C2 is the mixture between D1 and S1. Then it is the pressure is increased using the second pump. from T2 to D2, and D2 will be at the pressure PS2, and so D2 will be somewhere there. D2 will be mixed with the second extraction S2, and once again the mixture point will be much closer to D2, and for example we can consider then this mixture point that was called T3 is somewhere there. Then there's the third pump that will increase the pressure from T3 to T4, and so to D3, sorry, and D3 will be at the pressure PS3 and close to C3. Then we have the third mixture between the third extraction and D3, and we will find, for example, somewhere there the mixture that was called point C4. Finally, the last pump is increasing the pressure from C4 to D4, and D4 will be at the high pressure of the cycle here. And last step, the flow from D4 will go through the vapor generator in order to increase the specific enthalpy, and this will increase first the temperature to the saturation temperature, evaporate, and then superheat the fluid until point A. So, how to understand the effect of this on the cycle efficiency? I think the best way would be to plot schematically a few iso-enthalpy lines. The iso-enthalpy line has a shape going down, and so, for example, the iso-enthalpy line that is crossing point A will have a shape like this. So that will be specific enthalpy of point A, and similarly, the one that one that is going through point D1, that is crossing point D1, will be like this, the specific enthalpy of point D1, and the specific enthalpy of the fluid entering the vapor generator, so at D4, will be like this. So, if we did not perform any extraction, the fluid that would enter the vapor generator will be at the same specific enthalpy than C1 and D1, but under high pressure. Now, thanks to the preheating with the extractions that we had, the inlet of the vapor generator is the specific enthalpy of D4, which is quite higher, and so the difference left in order to heat up the fluid to the inlet of the turbine is lower than what we had before. The idea is to decrease the need of heating in the vapor generator, and that's what we have on the lower part of the ratio that defines the efficiency of the cycle. So, moving the inlet of the vapor generator from here to there will decrease the needed amount of heat that we have to bring to the vapor generator. But that's not all, because in fact there's also a side back. It's also decreasing the amount of technical work that is recovered from the expansion, and this is due to the fact that not all the fluid will be expanded from the high pressure to the low pressure. So the fact that we have extraction does that part of the fluid will not be fully expanded, and so it will decrease also a little bit this technical work exchange inside the turbine, and so decrease also what we have in the upper part of the ratio that makes the efficiency of the cycle. But overall, even if it decreases the upper and the lower side of this ratio, the total efficiency is generally improved and increased when performing extraction on a Hirn cycle.